Today we are going through the last part of the last example of the last bulk of the last chapter. So after the first lecture here, you will then be gurus when it comes to bond graphs. We are missing just one little point. Thereafter, it will be examples, examples, examples. Of course, you have to do a lot of examples to get this sort of under your skin, in your fingers, without thinking. So more examples then after the break, and well, I'll point out some elements with regard to the exercises, and then continuing with more examples tomorrow. Now, yeah, any questions before we begin? No? It's okay. Did I or did I not? Yes, I did. Okay, in chapter 6, we are seeking the state equation, the only needed equation to describe any system. To do that, you have to go through this working procedure with the causal strokes, starting with the sources. Then you could choose, if you had an I or a C element, you could choose, of course you always choose then the integral form, and then do all the mandatory strokes, continuing until you have done the entire bond graph. There were three possible outcomes out of this working procedure. One, the system is causal. All bonds have gotten a stroke, and all your energy storage elements, I and C, they are on the integral causal form. Everything is A-OK. Then we have some exceptions, and we saw the first one last time. It was over causal. One of the C or I element got the differential form, but that was not a big deal actually. You just had to sort of go the other way around. So for an over causal, for an I element, you got the stroke the wrong place. So instead of having a P dot with a circle around, you sort of have to go the other way around. You have a flow. And then what do you get up here? You get something time derivative of the flow multiplied with I. Also, the C element gets the wrong causal stroke. Okay, then not a Q dot down here and Q over C over here. It's the other way. So you have an effort, and then down here you will have time derivative of the effort multiplied with the value of C. So in practice, they will then not give another differential equation. It will mean a little bit more algebra. Because when you do this for the entire bond graph, you had somewhere else some P dot or a Q dot. And then these expressions here, the derivatives, when you do the derivation, you will have the same Q dot or P dot once more. So it will be a little bit more algebra, but no big deal actually. So they are not so difficult. Now, today, we are looking into the third nasty option, the third possible outcome when you're doing the causal stroke. You have a system that is under causal. So we jump straight to an example. How to handle an under causal example? Well, first of all, what is an under causal example? Well, you try to do this working procedure with all the causal strokes, but you end up with that you have some bonds that haven't received a stroke, and you're not allowed to choose strokes arbitrarily. It's some strict rules. So I'll show you here as an example. You have a force hitting some, say, a small plate or something without any mass. This plate is then attached here to a damper, and finally here we have a mass. and inertance. So it's a mechanical example. This plate will slide towards the ground here, maybe a thin oil film or something. So we have a linear resistance here as well. Here you have an R1, this damper R2, and an inertance, the mass. Find the bond graph and see how we can solve this one. Okay, start with the bond graph. I have here a plate. It has its own velocity, so I have a one junction. Then, well, actually, I have a little color. We can do it like this. Here, a one junction, and then this source attacking the one junction. That's okay. Here I have a resistance, so a 0 down to this R, and a solid wall standing still, like that. Here I have a damper inserted with a 0, and here I have something moving with its own velocity. Insert a one junction with an I element. And then we join all these. And finally, we need a source hitting this first one junction. So the raw bond graph should then be something like this. It's an effort source hitting a one junction without any mass. It's massless. From this one junction, you can go down, and here you find a 0 with an R1, and then a wall standing still. So this will be removed. We can simplify it directly straight to R1. Then we continue. Then I have a 0 like that. Let's see now. Here I have a one junction with only two bonds. Remove the one junction. We don't need it. So we can hook up directly here, and R2 and the mass. So there is my raw bond graph. Well, actually, it's simplified already. Everybody with me so far? That's okay? Yep.
In the event where you have the fluid replaced by a set of ties, in the other examples there's no resistance. Is that the way we...
Sorry, that we had no resistance.
Yeah, if in the event where we have a set of ties below, let's say, the mass,
Yeah.
there will be no resistance, right?
You mean this one here, if he had mass?
If you have ties below, for example, where you have the fluid.
Sorry, I don't understand. What do you call tires?
Let's say a roller.
Oh, here?
Yes.
Like this. No, you mean if you insert some smooth, nice rolling wheel there without friction. That's what you're talking about. Yeah, no. Well, it could still be friction if you had wheels, some resistance there. Then the detail could be a little bit tricky. I mean, then the resistance will be due to the rolling resistance, typically in the center for each wheel and so on. So that can be tricky. So what I imagine here is actually a linear damper, like a Couette flow in fluid mechanics. So you have one wall moving with a velocity, and inside here you have oil. What's the velocity profile? For a Couette flow, it will be a straight line going something like this. Okay, what's the force then you have to use to drag this upper wall at a constant velocity? Well, the force will be equal to the wall shear stress multiplied with area. The wall shear stress, that is viscosity, derivative of the velocity with respect to the cross-stream direction. And here this one is linear, so it will be equal to mu multiplied with velocity v divided by the gap h. There you see force will be proportional to the velocity. Linear damper. You see? But if you exchange it, this oil film, with wheels, then you have maybe a different type of resistance. It could be proportional to velocity squared, or yeah, something tricky. I don't know. That will be your choice. But normally then we would say the wheel are smooth and nice, they don't have any friction, then we forget it. Yeah. Other questions? Okay. Now try to apply the causal stroke on these bond graphs. First step, always all the sources. They are sort of unquestionable. Effort source has to be like that. It's the effort that hits the system. So the stroke has to be to the right. Okay, that doesn't dictate anything. Still have something undecided here for the one junction, but I have one I element. So I choose the correct integral form for him. But now you see that doesn't dictate anything either. For the zero junction here, we need just one stroke towards him. And this doesn't decide anything. And now you're stuck. You can't do anything else. You are not allowed to decide for yourself where the stroke should be for an R element. That's not allowed. You're not supposed to choose here. You can choose for the I and the C element, but not for the resistance. So these undercausal systems, they will typically arise when you have, say, plenty of resistances and not so many I and C elements. Then this can easily happen, that you will have a system that is undecided. Okay? So what do we do? How do we solve it? We have a trick. Undercausal examples can be solved by adding. And now we are going to add a virtual, either an I element or a C element. But of course then we are not going to add them with the wrong causal stroke. We are going to add them either like this or like this if it's a C element. So where should we add these to sort of help us here? Well, you know, for this one junction, he needs one stroke away from him. One stroke away from him. That means if we had a mass attached to that one junction, then he would be sort of satisfied. So adding and say virtual mass, virtual I to one junction, or if you look at a zero junction, he wants just one stroke towards him, just one. Okay, if we now add a spring, add a C element to that zero junction, then he would be satisfied. So we have either this one or a virtual C to a zero junction. That should help. And here, well, actually we have a choice. You could choose either one and it shouldn't make any difference. So let's try them both just to check that we get the correct result here. So whenever you have a system that is undecided, it's undercausal, you add a virtual element. For this system here, I said this physical plate had no mass. That's obviously a lie. Everything has a mass. So that might be physically smart to say, for this element here, I will now add a virtual mass, I virtual. So maybe a very, very small mass. I mean, it's easy to imagine that, yes, he has some mass. Okay. Then all of a sudden I have gotten another I element here. And of course I choose causal stroke. Then this one junction, no, sorry, my mistake, not here. Of course, away from him. Then this one junction has gotten the one and only away from him. Hence, the rest has to be towards him. Then we have stroke, stroke, and now also the 0 is satisfied. He has gotten the 2 strokes here away, then the last one must be towards him. So there you have the bond graph, and now the system is causal. But the virtual element there is a little special. So I just redraw it a little bit bigger. We have one junction and then up to this virtual mass down R1, continuing to a 0, and here we had a real mass, and then finally R2, like that. And the strokes were like this, and finally this. Okay, now find the equations, meaning annotate this bond graph. Put on all the efforts and flows on all bonds. Well, for the source, that's not a problem. I know the force there, and I don't care about the flow. I have one I element here with the correct integral form. So a P dot circle on the other side. P over I. What about this virtual thing? Well, this virtual, he is not supposed to give us another equation. So he does not get a P dot with a circle around him. To mark it, I put a 0 here, and then a circle around it. So he's not giving us nothing. So I put 0 for the effort there. But he will have a flow. I call it a virtual flow. Remember, he doesn't actually exist. And now with 0 on one side, you have 0 power on this bond. So actually he's not there. So this virtual flow, that's just an algebraic trick to solve the equations system here. So you'll see. Okay, but now we can't really go any further unless we started to think here a little bit. And starting with this one junction, who decides the flow? That's where you're missing a stroke. So it's this virtual flow actually. So that must then be here, and also the x if you like. Then for resistance number 1, if I know the flow, I can find the force on the other side, R1 times this effort. The virtual flow. Okay, what about this 0 junction here? Who decides the common effort? That's where we have a stroke. Okay, then I'm going to need the effort here, but I don't have it. But I can get it. I can find the flow on the other side, can't I? Because I know these two flows. So I can use the summation rule for the flow around this 0 junction. What comes in equals what goes out. So what we have here must then be Fv minus P over I. That must be the flow down to resistance number 2. And then on the other side, okay, that's just multiplied with R2. So here, R2 multiplied with Fv minus P over I. And that will be the effort that you find here. and also for the P dot, clearly. Now, have I done something wrong here? No. Should be okay. R2. FR. No, that can't be right. That can't be right. No, it should be correct. Should be correct. Let's continue. You should never think. Much better if you leave your head. Don't use your head. Just continuing. Okay, so now, as you see, all bonds are annotated. All the flows, all the efforts are here. Where's the equations? Well, I have one equation, because the common effort around this zero junction, that was this strange expression here. But I had P dot there already, so P dot has to be equal, and then this R2 F virtual minus P over I. So there I actually have my ordinary differential equation, just the one, because what's the order of the system? Well, it's a first order system, isn't it? I only have one real mass here. This virtual thing, it doesn't exist. So I have one equation, but I have two unknowns. This virtual flow, what's here? What's he supposed to be? There we use the summation rule around the other junction. The sum of the effort has to be 0. Okay, what comes in, that is the force, equals what goes out. And on the other side you have 0. Can I write that one as well? Plus we have the effort for resistance 1, R1 F virtual, and then finally plus this R2 FV minus P over I. There we have it. So the second equation is just an algebraic equation for the virtual flow. From this one you can find FV equal, and then finally insert it into this one. That one is going to take some time, so I won't bother you with it. Yeah, you can do the algebra yourself if you want. Any questions to that one? Yep.
Could you add more than one virtual element?
Could we add more than one virtual element? Oh yes, that's quite correct. Yes, you can. But of course, you don't add more than you need. Remember, as soon as you have another element, another stroke, then if you remember the working procedure, the step 2 there, you have to go back and then do all the now mandatory strokes. And then if the bond graph is complete, then you don't have to add anything else. But yes, if you have a very big system, maybe you need to add more than one, yes. Then you have to be careful here. F virtual 1, F virtual 2, F virtual 3, for instance. That could happen, yes. Like, I know some of you went into this trap when you had a bond graph, say with more than one mass, for instance. So you have an I1 here, and down here you had an I2. And then you had a P dot circle, P over I, P dot circle, P over I, and then you are in trouble. So remember then, P dot 1, P dot 2, they are totally different. And here P1 over I1, P2 over I2. It will be two different differential equations. Same with the C elements. Other questions? Yep.
So wouldn't we get the same result if we choose the R1 instead of adding with
yes, can we choose differently? Yes. Should be possible, shouldn't it? So let's try. Now, I took the first one. I added a virtual I element to a 1 junction. Try the second one. Add a virtual C element to the 0 junction and see what happens. A virtual R element doesn't help. I mean, he doesn't decide anything. He doesn't dictate anything. So you have to add either an I or a C element that sort of decides where the stroke should be. So now I add a C element here to this one, C virtual. So now what? We will have the effort hitting a 1 junction, R1, continuing to a 0 with now a virtual C, I element, R2. Here we go. Now what? Try the causal strokes. Start with the effort, and we could take the first I element, and then we were stuck. But now with this virtual C element, well, he has a stroke here. Then this 0 dictates the following. The rest of the strokes away from the 0 has to be like this. And then also you see the first 1 junction now has been decided, the 2 towards him, the final one down here. Okie doke. Now annotate the graph. We have the force and we don't need the flow. I have here again P dot circle P over I, so that's okay. And now for the virtual spring, the virtual C element. No equation from him. So he gets a 0 and a circle around it, not a Q dot. But on the other side, we need an effort, and virtual effort, E virtual. And you can now see instantly around this 0 junction who decides the effort. That's where you have the stroke. It's going to be this E virtual actually. Strange, strange, strange. Let's see, I can get rid of this one. No questions for here. Okay, right? So E virtual will come here, it will come here, and it will come here where I have a P dot. So that is my first equation. P dot equals E virtual. Okay. When I have the effort here, I can find the flow on the other side. That must be E virtual divided by the resistance R2, like that. Then we are missing something here around this 1 junction. Who decides the flow? So where you're missing a stroke. We need the flow here. I don't have the flow there. Well, find it. How do you find it? Well, you have the 2 efforts. So we can use the summation rule around this 1 junction to find the effort here. What comes in equals what goes out. So the effort here must then be F minus this virtual thing. So there, what comes in equals the sum of these two. Yes. Then I can find the flow. just divide by R1. So here you have F minus virtual effort divided by R1. And the same flow you will now find instead of the X, if you like, and also here. I don't have space enough here, so he goes there as well. Now, I actually have one equation for the derivative. So that's an ordinary differential equation. But I'm missing the algebra equation describing what this virtual effort is. So the summation rule around the zero junction, the sum of all the flows has to sum up to 0. So what comes in, that's this F minus E virtual by R1 equals what goes out. Here is a 0 flow out. And here I have P over I. And finally the flow down here plus E virtual over R2. So from the last equation, with some algebra, you can find this one on the form E virtual equal. And then you just insert this one here. And you find an expression for P dot. Now, if you do that correctly, and same with this one, you found the virtual flow, insert here, you will have something, then these should be identical. Of course they should be. The expression for them were a little bit messy. I can write it up for you if you want to do the test yourself. What did I find here? It's a little bit messy expressions. Force by R1 minus P over I divided by, what is it? 1 over R1 plus 1 over R2, something like that. So you can check it if you like. Any questions to that one? It's okay. So the trick, fairly easy actually. You add a virtual element, either an I on the one junction or a C or on a zero junction. That's it. Just remember the algebraic tricks then. When you insert these virtual elements, be sure that you give them a 0, not a dot, not another equation. That would be terribly wrong. Well, actually not so terrible. I mean, what have we done here? I've added a spring on this 0 junction here. So that might be reasonable actually, that you have a small spring here. Or maybe better, the first one, we said a virtual mass, that this plate actually have a little bit of mass, physically not so stupid. So, well, it really doesn't matter for the mathematics, but physically it makes a little bit sense. But either way will work. You will have a chance, if you pick the right or wrong problem, in exercise 4. That is out now. I will show it to you after the break. Okay, with that we should be done with the bond graph theory. So now everything should be crystal clear, I hope. So of course you're going to need a lot of examples, not a lot of exercises to sort of get used to the ideas. And especially I would think when you do the annotation, that can be a little bit tricky. when you are missing something that you really need. Like here, you wanted to find, okay, the common flow around this one junction. Yes, it should be from here, but you didn't have anything here. Okay, then you have to construct it using a summation rule. And when the bone graphs gets a little complicated, it can be hard to find. But a little bit training, it should be there. So now you should be capable of jumping into the most nasty problems. But as I said, exercise 4, very simple, simple problem. So there you can play around with different types of energy domains, mechanical, rotational, fluid, electric, and get used to how to deal with bond graphs for the different problems. Okay, no questions? Then we take a break and see if I can get the computer running in the meantime.